Thank you, Lisa, for the nice introduction. Hello, everyone. When I talk about this work, it's joint work with my postdoc at Peihan and an undergrad student at Bangkok. This is going to appear at Crypto this year. So let's start with a simple example. Let's say Alice and Mao are two cryptographers. They meet on Zoom for the first time, and they want to figure out who are their mutual friends, who are in common. For example, there is a list of Alice and Mao friends. They want to figure out who are in common. What can they do? Well, Alice can simply send all her friends to Bob. And this way, by comparing these two lists of friends, Bob can easily figure out, for example, Charlie and I are their common friends. But this way, Alice has to reveal all her other friends to Bob. And the cryptographer, she might not be willing to do that. So what can we do? Instead, we know that there's this tool called MPC. We can just run the MPC protocol, in fact, the 2PC protocol, to figure out their common friends without revealing any other information to each other. So this is a special case of secure 2PC, and you can formalize it as this problem called private set intersection, or PSI for short. In this case, each party has a private set of elements, and they're interested in learning the intersection of the two sets without revealing any other information to each other. This is a special case of 2PC with a very, very simple functionality, but it actually has found a lot of applications in practice. For example, if you're using the Chrome browser, you might have been notified from time to time about your leaked passwords over the internet. So how does Chrome detect your leaked passwords? Does Chrome have access to your passwords in the clear? Well, they actually run the PSI protocol. In this case, the two parties are the Chrome server and the user, where the Chrome server has a list of username and password pairs that are leaked over the internet because of data breaches. And the user has a set of username and password pairs that he is using himself. So the intersection of the two sets are exactly users' passwords that are leaked over the internet. So this is a perfect fit for PSI. And I just wanted to briefly note that in this case, we're dealing with unbalanced sets, where one set is significantly larger than the other set, and we want only one-sided output, only the user to learn the output. Okay, and this is also deployed on iOS, Keychain, Microsoft Edge, and Mozilla Firefox, and so on. Another application I wanted to mention is online advertising measurement. And this is also deployed by Google. In this example, the two parties are an ads platform, for example, Google, and an advertiser, let's say State Farm, which is an insurance company in the US. So Google has a list of users who have seen ads on Google about State Farm. And State Farm has a set of customers who have made a purchased insurance at State Farm. And the intersection of the two sets are exactly the users who have seen ads on Google and then end up making a purchase. And this is what we call ads conversion. They're interested in learning the ads conversion without revealing extra information to each other. This is another perfect example for PSI. And in reality, sometimes they're not allowed to learn the actual intersection for regulations reasons. Instead, they're only allowed to learn some aggregate statistics. For example, PSI cardinality, they're only allowed to learn the cardinality of the intersection, the size of the intersection. Another example is PSI sum, where in this set, along with each element, there is an associated value, which could be the amount of their purchase. And we're interested in learning the summation of all these associated values for all the elements in the intersection. This is another area. And PSI has found other applications. For example, Signal uses it for privacy-preserving contact discovery, JP Morgan uses it for privacy-preserving inventory matching, and so on. So if we look at the literature of PSI, there has been a long line of work under different frameworks, different group approaches in different settings, and so on. I might have missed some important work in this slide. When I make this slide, I feel like it's almost as hard as fitting all the different FPC frameworks, different FPC works in a single slide. As you can see, this entire area has been growing extremely fast, especially in the last few years. And I think partially due to the fact that it's being deployed in more and more applications, it's finding more application scenarios, and there is just naturally more excitement from both academia and industry. With all this effort, now if you want to do plain basic PSI, you can do it very efficiently for millions of elements within a few seconds. And now, if you talk to a broader community in industry or academia, people would, about this idea of computing setting transaction privately, people would naturally come up with potential applications in their own areas. But the question that often comes up, that is less addressed in our community, less explored, is whether you can do fuzzy match. Because most of the PSI works are focusing on elements being an exact match, they're exactly the same. But in a lot of situations, you might be dealing with a fuzzy match. For example, perhaps with bridge alert, users might have typos, and you might still want to see potential fuzzy matches. In ads conversion, you might be dealing with fuzzy PII information. PII stands for personally identifiable information. Like, for example, you might be dealing with addresses that are essentially the same, but they're in different formats and so on. So you're dealing with fuzzy matching. And naturally, whenever you're dealing with biometric matching, like fingerprint, facial recognition, it's always a fuzzy match. And here's another example for fuzzy geographic matching. Say that you want to do some sort of privacy-preserving ride sharing. On the one hand, you have a bunch of passengers. On the other hand, you have a bunch of drivers, and you try to match them, but it's a fuzzy match. In particular, you're trying to find all these pairs of passenger and driver such that their distance is less than some threshold under a certain distance metric. So how do we do this sort of fuzzy matching in PSI? Well, a naive approach is to reduce to plain PSI and use all these techniques that we have developed for plain PSI. Now, in particular, Alice is going to enumerate all the nearby points to form a new set, which is a little larger, and then run this PSI with false points. Okay, so this is a little unbalanced because Alice's set is larger than false. And then we reduce to plain PSI perfect. But the issue is that the computation and or communication cost has to grow with this larger set, this entire volume of this set X, which could be expensive. A recent work by Gary Garamella, Mike Roslick, and Jasper C. At Crypto22, they introduced this notion called structure-aware PSI, which tries to leverage the fact that Alice's set X is a structured set, where the structure is publicly known to both parties. In this case, it is a union of multiple high-dimensional balls, and this is known to both parties. So by leveraging this publicly known structure, they can develop a new protocol where the communication cost only grows with the description size of X, rather than the entire volume of X. So the drawback of their work is that Alice's computation still has to grow with this entire volume of X. Alice's computation is still large. So the natural question to ask is whether we can achieve both computation and communication to only grow with the description size of X. And this is the key question that we have tried to address in this work. And there are a lot of other limitations of prior work. For example, they can only deal with union of disjoint balls, and in fact, they have to be a little far apart. Can we deal with like overlapping balls? And second, they can only work with, they can only support. Okay, never mind. They can only support plain PSI. So can we support the PSI with extended functionalities like cardinality or so on? And they only allow Alice to learn the output. Can we allow Bob to learn the output? Because that might be needed in some applications. And last one is they only support semi-automated security. And this last point was addressed in the follow-up work by the same set of authors at Quinto last year. They achieved malicious security, but they have the same the other limitations as before. Okay. But a key advantage of their work is that they only use very lightweight crypto. They only use lightweight crypto, in particular, only PRGs and hash functions, plus all transfer, which again can be instantiated very efficiently using OT extension, silent OT extension, and so on. So it's very lightweight, everything is very efficient. Okay, and we want to keep this advantage. And here's our results. So we achieve structure-aware PSI where both computation and communication only grow with the description size of X. And we address all these other limitations as well. We can deal with overlapping balls, PSI, both plain PSI and PSI chromatic and PSI sum. We can allow either Alice or Bob to learn the output, but we only achieve semi-omni security, and we leave Million-share security for future work. And we keep the same advantage as before, only lightweight symmetric key crypto plus OT. There are little caveat in this result, in particular when we deal with PSI chromatic sum or Bob learning the output, it only works for this ring balls, and you will see why they win this one. In this talk, I will focus on this main result, how we achieve both computation and communication that only grows with the description size of X. And we'll briefly mention these extensions at the end of the talk. Before diving into our techniques, I want to be a little bit more specific. What do I mean by description size? What do I mean? What is the distance metric that we consider? Okay. So the distance metric that we consider in this work is L infinity norm, which is the same norm considered in prior work. Let me briefly remind you what is L infinity norm. So we're considering a d-dimensional space. If you think of 2 points, x and y, each has d coordinates. So x is x1 to xd, y is y1 to yd. And the L infinity norm distance between x and y is defined as the maximum value of all the distances between each dimension. And we want this distance to be less than some threshold delta. And if you visualize this, it roughly looks like this. You have a point x in a 2-dimensional space. So all the points within distance delta in L infinity norm form this square of diameter delta, radius delta in each dimension. In a high-dimensional space, it's going to be a d-dimensional hypercube of radius delta in each dimension. And for the rest of the talk, I will using a slightly different notation. Instead of radius, I'm going to consider this 2-dimensional or high-dimensional hypercube of diameter delta instead of radius delta. It's essentially the same thing, just thanks to its easy notation. And then we're going to consider this d-dimensional space where each the domain of each dimension is of size u in each dimension. Okay, so this is the notation I'm going to use for the rest of the talk. So prior work, GRX22 and GRX23 follow this paradigm, which we also follow, where they start with a single ball, single point structure where PSI, where Alice has a single ball, single structure, and then Bob has a single point, and they want to run PSI. And then they have this spatial hashing technique to extend this construction to multiple multi-point, where Alice has multiple balls and Bob has multiple points. And in our work, we improve both components. For single ball, single point, we improve the computation and communication so that they only grow with the description size of the structured sets. And for spatial hashing, we also have new techniques to improve the concrete efficiency. And then we can also deal with overlapping balls. For the rest, here's the comparison. Here's the more concrete comparison for a single ball, single point, in terms of computation and communication, comparing our work with GRX22. And here are the parameters, along with some example numbers, just to give you some sense of the scale. So lambda is a security parameter, and in fact, some of the security parameters are statistical security parameter, but I'm not differentiating between them. I'm just for simplicity. Okay? And D is the dimension of the space that we consider. Delta is the diameter or the threshold that we consider. U is the domain size in each dimension. And this is the comparison for computation, Alice's computation and Bob's computation. And remember, we only use lightweight crypto. So we count the number of PRGs and hash operations. So as you can see, Alice's computation in GRX22 has this factor delta to the D, which is the volume of the high-dimensional ball. So it has to grow with the volume of the high-dimensional ball, which we get rid of in our work. But on the other hand, in our work, Bob needs to do a little bit more computation, in particular log U to the power D. And in terms of communication, it has two components. One is the all-radius transfer, And then after that, Bob needs to send one more message to Alice. So the OT cost in terms of communication is the same as before, but Bob needs to, in the last one, Bob needs to send more information to Alice. So at a very high level, Bob is going to do a little bit more computation and a little bit more communication, but Alice's computation is reduced significantly. And this is a single ball, single point in this entire universe. And in fact, after we apply the spatial hashing to achieve multiple multi-point, we don't have to consider this ball in the entire universe. We just need to consider this mini universe of order roughly delta. So all these U's will become delta in the final complexity. But so the efficiency will be better, but the prior work still has this delta to the D factor. So it still has to grow with the entire volume of the ball. And in the paper, we also analyze the efficiency improvement in terms of spatial hashing and multi-point. It's more complicated and I'm not going to go into details. And we also collected concrete numbers to showcase some concrete efficiency improvement. We just wanted to note here that we're comparing with both GRS22, the semi-honest one, and GRS23, the malicious one. It's because GRS23 actually first improved the semi-honest one and then turned into malicious. So we're comparing with their semi-honest version. All right. But I do want to mention that there's another work by Barton who, as you look at this year, they also achieved structure-aware PSI with this much computation and communication complexity, where it grows linearly with the diameter delta and exponentially. But they use very different techniques. They use public key crypto from decision DP Hubble assumption. In particular, they rely on the homomorphism of alpha encryption. But they can deal with other distance metrics like L1 norm, L2 norm, and so on. Very interesting work. All right, but I'm not going to compare with that in this talk. All right. Okay, so for the rest of the talk, let's start into the techniques. How can we achieve this? I will be mostly focusing on the single ball, single point, because it will highlight most of our technical ideas, and then I'll briefly mention the other extensions at the end of the talk. Okay. So single ball, single point, I will start by explaining the construction of prior work, where they constructed structure-aware PSI from two components. One is function secret sharing, the other is obvious transfer. And then we constructed structure-aware PSI using roughly the same idea, but from incremental FSS. Okay. So let's start with that work. I will briefly recap everybody what is FSS, what is OT, and then show you how to combine them to get SA-PSI. And hopefully, after that, you will also have a better understanding of why it has the limitations that I mentioned earlier. Okay, what is FSS? The function secret sharing is a notion introduced by Warren Gilbert and Peihan back in 2015. So say that you have a function f from some function family which has a domain D and output a single bit. You can split this function into two shares that satisfies three guarantees. First, correctness, which says these two functions add up to f on every input. They just add up to f. For any input x, f of f0 of x plus f1 of x is equal to f of x. And second, privacy, which essentially says each individual share looks completely random, completely hides the function to be shared, or it's simulatable. And finally, succinctness, which says the description size of each individual share is very succinct. It's significantly smaller than the domain size. This is function secret sharing. And now we're going to consider function secret sharing that captures a structured set. What do I mean by that? So I'm going to consider a function that outputs 0 on all the points in the structured set, and 1 everywhere else. Okay, so it looks like this. If you split this function into 2, then you have a guarantee that for any point in the set, f0 of x is going to be equal to f1 of x, because they add up to 0. For any point not in the set, you have a guarantee that they evaluate to different values, because they add up to 1. Okay, so this is that as a construction set. The other component, also many other components, of the transfer is especially TPC between sender and receiver. The sender has two messages, and 0 and 1 and arbitrary messages. Receiver has a single choice bit as input, and from OT, the receiver will get one of the two messages depending on his choice bit, and sub B, and the other message is completely hidden to him. And the sender learns nothing. The sender has no idea which message is transferred. And we all know that OT can be instantiated very efficiently using OT extension, 7th OT extension, and so on. It's very efficient. Okay. Now we have our components FSS for structure and set of image transfer. Now let's see how we can combine them to get single ball, single point as a PSI, where Alice has a single structure S, and Bob has a single unstructured point Y. Right? Okay. So here's roughly how it works. We're gonna run obvious transfer while Alice is the sender and Bob is the receiver. Alice is gonna prepare this function single share, this FSS, for her structured set, split into two shares, and feed into OT. And then Bob is gonna randomly sample a choice bit B and feed into OT. So Bob is gonna get one of the two shares. And then he's gonna evaluate this share on his input Y. Okay? What guarantees do we have? First, for any input Y, if Y is in the set, then we know that f0 of Y is equal to f1 of Y, which means f of Y is kind of computable or predictable by Alice. So Alice also knows Y. Because f of Y is going to be the same regardless of the choice bit. On the other hand, if Y is not in the set, then f0 of Y is going to be different from f1 of Y. So f of Y is going to be unpredictable. It will look random to Alice, because it could be f0, it could be f1. Alice has to guess the choice bit. And this is just a single bit. We're going to repeat it multiple times, and in fact, security parameter lambda times. We just repeat this OT, and then Bob is going to get lambda bits, one from each OT and FSS evaluation. And then he's going to concatenate all these bits together and apply a hash on top of it, and send it back to Alice. Now, if Y is in the set, then we know that each individual bit is kind of computable or predictable by Alice. So all these bits are computable, and this entire hash value is also computable by Alice. On the other hand, if Y is not in the set, each individual share looks random, they're unpredictable. So this entire hash is also unpredictable. Another look at that picture over there. For every point in the set, all these bits are predictable by Alice, so this hash value is also computable by Alice. But for every point not in the set, then every single bit is unpredictable by Alice, so this hash value is also random to Alice. So what Alice is going to do is that she's going to enumerate every single bit in her set. She's going to enumerate every single bit in her set, and compute all these bits and compute these hash values, and compare with this hash value sent from Bob to see if there's a match. If there is a match, then it must be the case that Y is in the set, and Alice can identify that point immediately. If it is not in the set, then it's just all the question marks and it looks random to Alice. So this is the construction of prior work. And if you think about it, hopefully you have a better idea why it has the limitations that I mentioned earlier. In particular, Alice's computation has to grow with X because she has to enumerate every single point in her set. This is expensive. And you can think about other limitations why that's the case. But how can we reduce Alice's computation? Our core idea is that besides this hash value, we're going to ask Bob to send a bit more information, a bit more hints, so that if Y is in the set, then these hints are going to guide Alice to find Y more efficiently. How do we achieve this? Next, I'm going to move on to our work. So what is incremental FSS? construct it, how to construct incremental FSS and so on. But I'm going to start with a very simple example, one-dimensional interval. Okay. To illustrate our ideas, and then we'll talk about how to extend it to d-dimensional hypercubes. All right. One-dimensional, and I'm going to consider even a simpler case, one single-dimensional, one-sided interval. Because we're in a one-dimensional space, and Alice's set is a one-sided interval. It's a one-sided interval. It's just 0 to alpha. And Bob's point is a single point y. And we're trying to run PSI. So if you think about it, it's essentially comparing y with alpha. And that's all we want to do. And the FSS approach that I talked about earlier is roughly this. You consider this function f of alpha that evaluates to 0 between 0 and alpha, and evaluates to 1 for greater than alpha. And you split it into two functions such that they evaluate to the same value, from 0 to alpha, and they evaluate to different values for greater than alpha. And then you run OT, you run hash functions, but the issue is that Alice has to eventually enumerate every single point in her set, which is computationally expensive. So how can we reduce it? Now let's take a step back and think about how are you going to do comparison with alpha? How do you do comparison with alpha? If you think about alpha as a bit string, you can build you can draw a binary tree, and this is how you traverse the tree from the root all the way to alpha. And this is kind of the critical path when you compare with alpha. And there are a few critical points here where you deviate to the left of the critical path. I'm going to call them critical prefixes. So they're critical because once you deviate from the critical path to the left, you know immediately that you're less than alpha. You don't have to continue. You're done with your comparison. For every point, for example, this point here, which is less than alpha, it must be overlapping with one of the critical prefixes. It must be deviating to the left at some point. Okay? So you think about it, it feels like you don't have to evaluate all the way to the leaf to compare with alpha. You can sort of terminate earlier if you can get some information earlier. And this observation leads us to this solution called the incremental FSS, where besides the leaf nodes, you also get output for all these internal nodes, for all these prefixes. So you're essentially splitting this entire tree into two shares, such that for everything to the left of the critical path, they will evaluate to the same value. For everything on the critical path and to the right of the critical path, they're going to evaluate different values. And this idea of incremental FSS is not completely new. A prior work by Bonet et al. At Oakland 21 introduced this incremental DPF for distributed point function, and we extended this notion for structured set. Okay. Given an incremental FSS, let's see how we can improve our structural work. So we're still going to run over-base transfer, where Alice is going to prepare incremental FSS, splits into two shares, feed into OT. Bob gets one of them. And now Bob is going to evaluate this share on every prefix of his input. So he's going to get one value per level of the tree. What guarantees do we have? If y is in the set, then it must be overlapping with exactly one of the critical prefixes. And after that, it's all going to be computable by Alice, because they all evaluate to the same value between these two trees. On the other hand, if y is not in the set, then all these nodes are going to look random to Alice, because they all evaluate to different values between these two trees. And again, I'm going to amplify it by only lambda times. But now, Bob is going to compute more hash values. Okay? He's going to compute more hash values, one per level of the tree. In particular, the first hash value is going to be computed on all these leaf nodes of these trees. And then the second computed on the second level of the trees, and third level of the trees, and so on. And the last hash value is going to be computed on all these leaf nodes of the trees. And then send all these hash values, log of them, back to Alice. And now on Alice's side, if y is in the set, then it must overlap with exactly one of the critical prefixes that can be computable by Alice, which means there must be one hash value here, that is computed on that critical prefix that can be identified by Alice. So Alice knows immediately that y is in the set. And we're almost done. Okay. So Alice knows that y is in the set, but how can she find y efficiently? How can she find this intersection? Find y. If you look at this picture again, actually all these nodes after the critical prefix are also computable by Alice because they all evaluate to the same value between these two trees. So Alice can just do a simple binary search using these additional hash values sent from Bob, like hints, because they have one hash value per level of the tree. So you can just do a simple binary search to find y. And then we're done. If you look at this protocol, you might be thinking, does it actually leak more information to Alice? Because it seems to reveal where you deviate from the critical path. When you think about it for a second, this information is actually revealed to Alice from, it's implied by the ideal functionality of PSI. Because if y is in the intersection, then Alice learns y in the clear, learns the entire y. So she knows exactly where you deviate from the critical path. So this is not revealing any other information, any information more than what is already implied by the ideal functionality. And we're kind of exploiting this fact in this protocol. On the other hand, if y is not in the set, as I mentioned, all these nodes are going to look random. So all of these hash values are just going to look random to Alice. And then we're done with single dimension. I haven't told you how to construct incremental FSS, but I will talk about later. Now, I first want to talk about how to extend this simple idea to d-dimensional hypercubes. Okay, it's a little bit more tricky. How do you do early termination? Okay. And again, I'm going to show you a very simple example, two-dimensional, one-sided interval. But the ideas can be generalized, can be extended to higher dimensions. Okay. So we consider a two-dimensional space, and Alice's set is this lower left corner here. So she only has two inputs, alpha 1 and alpha 2. And Bob's input is a single point with two coordinates, y1 and y2. And they're running PSI on this. So we're essentially comparing if y1 is less than alpha 1 and y2 is less than alpha 2. But if you think about it for a second, this idea of early termination that we talked about earlier does not trivially work here. Because you cannot trivially terminate if the first condition is met. Because it could be the case that the first condition is met, but the second condition is not. In that case, you shouldn't reveal any information. You cannot just trivially terminate. So how do we deal with this? Now, again, let's take a step back and think about how would you do high-dimensional comparison. When you do two-dimensional comparison, compare y1 with alpha 1, y2 with alpha 2. So if y1 is less than alpha 1 and y2 is less than alpha 2, then it must be the case that y1 overlaps with one of the critical prefixes in this tree, and y2 overlaps with one of the critical prefixes in this tree. So there must be one prefix of y1 and one prefix of y2 such that both are critical prefixes. So it's kind of like a two-dimensional critical prefix. And we're going to try to identify this two-dimensional critical prefix in our protocol. Here's how it works. We're still going to run OT, and Alice is going to prepare two incremental FSS, one for alpha 1, one for alpha 2, feeding OT. Bob gets one share for alpha 1, one share for alpha 2. and then he's going to evaluate the first share on all the prefixes of y1, the second share on all the prefixes of y2. And then Bob is going to consider all the pairs of prefixes of y1 and prefix of y2 and concatenate them. So if y is in the set, then we know that there must be one prefix of y1 and one prefix of y2 such that both are critical prefixes. Both are computable by Alice. On the other hand, so this concatenation is also computable by Alice. On the other hand, if y is not in the set, then there must be at least one dimension where all these nodes are random. They're all unpredictable by Alice. So this concatenation is also unpredictable by Alice. And then we're gonna repeat this multiple times, number of times. But Bob is gonna compute more hash values. He's gonna compute one hash value for every combination of a prefix of y1 and prefix of y2, quadratic number of them. For example, the first hash value is computed for I equals 1, j equals 1, which means all the root nodes of the first trees and all the root nodes of the second trees. Concatenate all of them together. And then the second hash value is going to be computed on I equals 1, j equals 2, which means all the root nodes of the first tree and all the nodes from the second level of the second tree, concatenate them, and so on. And send all the quadratic number of hash values back to Alice. And now on Alice's side, if y is in the set, then there must be one prefix of y1 and one prefix of y2. Both are critical, both are computable by Alice, which means that there must be one hash value here that is computed on this two-dimensional critical prefix that can be identified by Alice, and Alice can conclude immediately that y is in the set. And the remaining question is how to efficiently find y. And looking at this picture, all these nodes after the critical prefixes can also be computed by Alice. So she can again do a binary search bit by bit and then dimension by dimension. And then we're done. Right? On the other hand, if y is not in a set, then we know that there will be at least one dimension where all these nodes are random to Alice, they're unpredictable by Alice. So among all these hash evaluations, there will be at least one dimension that is unpredictable by Alice. So all these hash values will be safe. We'll just look at them. All right. Cool. One remaining question: how to construct this incremental FSS for our needs? Well, these ideas can be extended to d4s1-1, and we're almost done. The only question is how to construct incremental FSS. Okay. Our starting point is this distributed point function from prior work, which is a special FSS for this point function. If x is equal to alpha, then it outputs 1, otherwise outputs 0. And you split this distributed this point function into two shares. It's very, very high level. The construction works as follows. So say that you have a length WPRG, and you're going to construct two GGM trees. You're going to construct two GGM trees with the following guarantees. So this is the critical path when you do comparison with alpha. And between the two trees, it has a guarantee that if you are on the critical path, then the PRGCs are going to be different between these two trees. But if you deviate from the critical path, once you leave the critical path, then all these PRGCs are going to be the same. To achieve this, they attach an additional bit to every node of the tree, which you can think of as an indicator bit, indicating whether you're done with your comparison or not. And if you're on the critical path, then these two trees have different indicating bits, indicating that you haven't done your comparison yet. But once you deviate from the critical path to the left or to the right, then the indicator bits will be the same between these two trees, indicating that you're done with your comparison. And they have additional projection strings and metrics to make it happen. It's a very beautiful construction. Starting with this construction, the idea to achieve what we need, incremental distributed comparison function that looks like this, it's a very simple idea. We just attach one more bit to each node as the output that we want. And we achieve this guarantee that if you're on the critical path, then these output bits are different. If you deviate from the critical path to the left, then these output bits are going to become same, and they will keep being same. If you deviate to the right of the critical path, then these output bits are going to be different, and they will keep being different. That's the high-level idea. And if you're familiar with the previous UPF construction, this will be an easy exercise for you. All right, cool. For the last 10 minutes, I want to briefly mention a few extensions. So first, I want to mention an observation, simple observation that can help us handle overlapping balls. All right. To say that Alice has a union of balls, how do we handle it? How do we handle union balls? The way that firework handles union balls is the following. They constructed a new FSS for the union of balls. The outputs 0 on every point in the union of the sets, and outputs 1 otherwise. So it looks like this. For any point in the union, and outputs 0, otherwise it outputs 1. And then they can construct this FSS by somehow composing FSS for individual sets in a particular way. But unfortunately, this composition only works for disjoint sets, for disjoint balls. So if you think about it, this approach is actually an overkill for PSI, because it additionally tries to hide which set X is in. So the thing about the ideal functionality of PSI, this information is actually implied by the ideal functionality. In particular, if you have a bunch of sets that are overlapping or not overlapping, and you consider this point Y here, this point Y here, if it is in the set, Alice learns Y in the clear, so she knows Y is in both S1 and S2. She knows this information. We don't have to hide it. And similarly, if Y is not in the set, then she knows that it is not in Y1, not in Y2, not in Y3. So we don't have to go through this FSS. Instead, we just run structural PSI for every single set. And that's enough for PSI. This is again exploiting what information can be inferred from the ideal functionality. This is a simple hour observation. In our paper, we have some new spatial hashing techniques to achieve better concrete efficiency, which also leverages this hour observation. Next, I want to briefly talk about PSI cardinality. Here, it's another simple observation where we can actually reduce structure-aware PSI cardinality to plain PSI cardinality, where Alice only needs to feed in all these critical prefixes, and Bob feeds in all these prefixes of all his points. As I mentioned earlier, if Bob's point is in her set, then it must be overlapping with exactly one of the critical prefixes. So we just need to count how many matches are there. There are a few caveats in this approach. First, it only works for disjoint sets, for disjoint balls, because only in that way can we guarantee that every point only matches one critical prefix. And the other thing is that among Bob's prefixes, there might be some duplicates. So we actually reduce to PSI sum instead of PSI cardinality, where along with every prefix, we attach an associated value indicating the number of times that this prefix appears in Bob's set. And then we're done with PSI cardinality. And then for the other extensions, we're essentially using similar observations. All right. Yeah, to summarize, we achieve structure-aware PSI with both the computation and communication only grow with the description size of that, but we can also handle these other extensions like overlapping balls, PSI cardinality, PSI sum, allowing Bob to learn the output and so on. And we have the same advantage as before, only lightweight symmetric crypto plus OT. Now I want to briefly mention some open questions. First, our computation and communication cost still grows exponentially in the dimension D. So it will be expensive if you're dealing with a large dimension. Now the question is whether you can reduce that to linear or polynomiality. The second question, all the techniques that I mentioned are very specific for L infinity norm. It doesn't work for any other norms. So can we develop efficient techniques for other norms, for example, L1 norm, L2 norm, edit distance, and so on? And I want to briefly go back to some of the motivating examples that I mentioned at the very beginning of the talk. Back then, you might be thinking, like, for example, the biometric matching, field beneficial recognition. I'm sure some of you must be thinking, oh, she's hand waving. It's just, it's not possible or it's not practical. But I'm not. So I think, based on my limited knowledge about ML, like, for example, how facial recognition works, you're actually running some neural networks, and you get two high-dimensional vectors, and you're essentially trying to figure out if these two vectors are close enough under some distance metric. So if you can develop efficient techniques for other distance metrics, then it's not just hand-waving. There's hope for being practical. Finally, I think one of the most interesting aspects of this line of work is this connection between FSS and the PSI. And in fact, we can weaken some of the guarantees from FSS for structured sets. For example, it doesn't have to always output a single bit. It can output a bit string. And then, for every point in the set, which we call yes instances, we want it to always output all zero string. But for all the points outside, it suffices if it outputs anything other than zero. And additionally, we can tolerate false positives in these no instances. We just run more OTs to compensate that. Okay? So these weakenings of FSS actually allows us to construct a more efficient FSS for high-dimensional hypercubes. So maybe there's hope that by looking at some of these guarantees, you can construct a weak FSS for a broader class of functions. And maybe you can capture other structures as well. And that concludes my talk.